Could you confirm my slide is visible to you all? Could you confirm the slide is visible? Could you please confirm the online students? My slide is visible. Audio is visible. Any one of online student can confirm my audio is available and video. Okay, let's start with our continuous of the presentation. So now I move to an uncompensated transmission line. I just showed you an example with the load. Now the next task is on the transmission line. So in a transmission line, the cables you will have resistance, inductance, capacitance, and G not in small, in kilometers. So if you want to look at a module of a single phase transmission line, you have a source voltage, which is the sending end voltage, and you have a receiving end on the load side. The transmission can have a long length, say the length of the transmission line is L, and the source current is IS. Maybe at a particular point, say delta X, a deviation of your distance from the receiving end, say delta X is the distance X from your receiving end, then you may have a current deviation I plus delta I, voltage may be V plus delta V on the receiving side, because the transmission line has an impedance. Because of the impedance, obviously you will have an effect of current small deviations at delta I and voltage deviation delta V. So this is a simplified representation of a transmission line of a single phase basis. Now I want to go inside and look at what is the voltage and current. So voltage of your transmission line, you will have voltage due to the receiver end into cos h rho x plus receiver and current into ZC into sin h rho x. So this is the formula for calculating your voltage. And this is the formula for calculating your current, which is VR divided by ZC into sin h rho x plus IR cos h rho x. So where Vx and Ix are the voltage and current at any particular distance, xa, x can be 1000 meters, 2000 meters, x is equal to. Then you can able to calculate. In this formula, what is the value of rho? Rho is nothing but your J into B. And it is a lossless lines, and it is an hyperbolic function like cos h rho x, cos h rho j beta x equal to cos beta x. We make it as an assumption to make the equation much simple. Similarly, sin h rho x is equal to sin h j beta x, all equal to j sin beta x. So we are making approximation and substituting all these values in the current and voltage, we can able to find a reduced equation in terms of cos beta and sin beta for your voltage and current. From this, I'm going to calculate what is beta, that is the in radians or wavelength of your electrical length of your lines, where beta equal to omega into root of LC. From this, we can able to say your beta is directly proportional to frequency. Omega is equal to 2 pi f and the root of LNC. Further, if you want to reduce this equation, you can have a look at 2 pi f by V. I put it, which is equal to 2 pi by delta. So delta is the wavelength of the light. V is the velocity of your light. So you know the values. If you know these values, you can easily calculate what is your beta of your transmission line. Then the characteristic impedance. What is the characteristic impedance of your transmission line, which is uncompensated? So in order to calculate the impedance of your uncompensated net, which is nothing but root of Z by Y, which is also given by R plus J omega L divided by G plus J omega C. If you have a lossless line, there is no loss, ideal condition, then RG equal to 0, then your impedance is only root of L by C, which is not practically possible. There is a loss in your transmission line. So if you consider a lossless transmission line, your ZC is going to be root of L by C. What is the general formula? It's nothing but the root of ohms per unit length divided by ohms per unit length, which is nothing but Z by Y. Then we get root of LC. So for example, the approximate value of your surge impedance for a overhead lines is 400 ohms. So if you have an overhead lines, you know the meaning of overhead lines, the national grids, you have 400 ohms standard surge impedances. For underground cables, which is around 40 ohm surge impedance, and for transformers is several thousand. So surge impedance of your overhead transmission line is 400 ohms, underground cables is 40 ohms, and for transformer is several ohms. Now, why we talk about surge impedance? Surge impedance is very, very important, a key role, because if the surge impedance of your load is very high, it can act as a shunt reactive absorber. So it absorbs all the reactive power from the system. If the surge impedance of your system is when the line is loaded below, if the seal is very below than the guidelines, then it will act like a shunt capacitor. So it will supply all the reactive power to the system. So your surge impedance can act as a absorb the reactive power as a shunt reactor. Of course, it can also generate the reactive power to the system as a capacitor. So that's why it's very important how to calculate your surge impedance in megawatt, which is nothing, which is calculated by the ratio of your line voltage V square divided by surge impedance. So in the formula, still, I mean, surge impedance or natural loading fully depends on the voltage because it's directly proportional to the square of the voltage. And the voltage in your high transmission lines or in kV and MV, and this is very important. So that's why SIL is not measured in a very high power lines. We can't able to measure, but it can be realized by the system operators. System operator has some guidelines. So when the line is loaded above, as I said, it will act as a shunt active reactive observer. When it is below the SIL value, it worked like a capacitor. So you generate MVA power to the system. That's why surge impedance of is very important in your transmission line. Do you have any doubts about surge impedance? Otherwise, I will go to the next slide. Then uncompensated line with open circuit. So you have a transmission line, but the transmitter line is uncompensated. You are not having any compensation. And if it is open circuited, what happened? So you know the general formula for your voltage and current. So voltage is given by Vx of x is nothing but Vs cos beta x divided by cos theta, where VR sending end voltage is given by so receiving end voltage is given by sending end voltage divided by cos theta, where theta equal to beta into L. L is your length of your transmission length. So how to calculate the current is given by imaginary part of your Vs divided by Zc into sine beta x divided by cos theta. So this is the formula for calculating your current profile equation. Now let us go inside to look overall equation. We are not looking at in detail. If it is an uncompensated network, if it is open circuited, what happens? Sending end voltage will be equivalent to your receiving end voltage. So Vs is equal to Vr. Then we use these equations. We are finding the resultant. We apply these equations and we are adjusting the parameter by trigonometrical additions. Finally, we find Vr into cos theta plus cos square theta plus sine theta divided by 1 plus cos theta. This is your sending end voltage. And sending end current is given by J times Vs divided by Zc into tan theta by 2. If assumed your sending end voltage is equal to receiving end voltage, and your sending end current equal to minus IR. So IR is the receiving end current. If you are going to measure at the midpoint of your transmission line from the generator towards the load, if you are going to measure at the midpoint, your midpoint voltage is given by Vs divided by cos theta by 2. Assume, as I said, VR equal to maximum voltage. Sending end voltage should be equivalent to the maximum voltage and receiving end current is 0. So this is an ideal conditions. For example, if your generator is under excited from the sending end voltage, you are making so then there is a variation in your sending end voltage because you are going to make under excited operation of your generator due to the line charging. So because your cables can work as a capacitor, in order to make it a decharging purpose, we make under excitation. For this purpose, what happened? Assume your receiving end current is 0, then the sending end reactive power is going to be I M, the maximum current, into Vs Is star. So this is the formula to calculate your reactive power of the sending end. Then how to calculate your line current at the sending end is given by J times the modulus of Vs divided by Zc into tan theta. How to calculate your power at the sending end? Minus P naught into tan theta. Most important is that, for example, if you have a 300-kilometer line, the QS is nearly 43% of your natural load expressed in MVA. So if you are designing for a 300-kilometer line, your QS, the reactive power from the sending end, is nearly 43% of your naturally expressed MVA. At 400 kVA, the generator could have been absorbed 172 MVAR. As an example, if you have a 400 kVA generator on the sending end, then it could absorb 172 MVAR. Can I go to the next one? So this is an example of an uncompensated network with a line under load. So when I put the load, what happened? First, we will see the diagram that can give you a clear idea. So in the x-axis varies in per unit from 0 to say 2 to 3, 4. Then this scale we measure P divided by P naught. In y-axis, we are measuring VR divided by VS, which is sending end voltage divided by receiving end voltage. So we are going to calculate, see the performances. As you can see, the variation of P divided by P naught increases. Your ratio between sending end to receiving end voltage also increases for different values of power factor. For example, this case 0.9 power factor lag. This is the case 0.97 power factor lags. This is for power factor of 0.9, say around 0.799. Then this is for a leading power factor 0.97. This is for leading power factor 0.95. Lead power factor. So we have both lag and leading power factor. This is around a unity power factor in the middle. So you can have a look how your variation of your P divided by P naught varies with respect to sending end voltage, receiving end voltage divided by sending end voltage. All the cases, if you keep on increasing your P by P naught ratio, at the end reaching beyond the maximum value or natural load, it's 100%. If you are reaching, again, all the value comes back to 1.08%. The percentage of ratio between receiving and sending end, as you keep on increasing your P by P naught, always return back to 1.088. If you look at the lagging loads and leading loads requires less P by P naught. You can have a look for a 0.09 power factor lag, 0.97 power factor lag. It requires minimum P by P ratio. Whereas for leading loads, P by P ratio is much higher, but again, it returns back to 1.088. It's clear to you. First, the real characteristics, how it could happen with a function of load and load power factor, how your receiving end voltage as a function of sending end. So at the maximum value of all the cases of your power factor, when P by P ratio is increased, you always land at 1.08. So that's why VR by VS is always 1.088% at rated, more than the rated P by P naught. How to do that calculation? Let us look at how the loads will have active power and reactive power on the receiving end. R represents the receiving. S represents the sending. So I calculated what is PR plus JQR. From this, I calculated what is my current. So P minus JQ divided by V. And this is the voltage formula. So based on these informations, I calculated all these parameters of the graph to illustrate the variation of your receiving end voltage with respect to power factor. For example, each case, you can have a load power factor. That is a maximum transmissible power. So maximum transmissible power always at 1. But still, if you keep in increasing, it goes to a ratio 1.088. The load power factor has strong influences on the receiving end voltage. You can have a look. We have a different characteristics for a lagging power factor and leading power factor. That's why there is a strong influences. So in case of uncompensated transmission lines, for example, it is going to be between 150 kilometer and 300 kilometer long operated system. the normal voltage provides the load power factor is high. So in case of the transmission line, which is having 150 kilometers and 300 kilometers, obviously the normal voltage has a very high power factor. So much compensation is not required. You don't want a compensator in your transmission line for small kilometers, 150 kilometers or 3 kilometers, 300 kilometers. The uncompensated system doesn't require a compensator because you get a very good power factor. Can I go to the next one? Now about the reactive power requirement, that's very important. Already we see if you are not having a sufficient reactive power, again you will collapse the power system. So in order to maintain that, how to do that? So we know the formula for the voltage, sending and voltage, receiving sending and current. We already know these formulas, and we already seen for the maximum power transmitted P, you should have a maximum active power and reactive power. This is a formula where we can get able to calculate Vm into Im star. If you keep Qm equal to 0, the reactive power is 0, then you get a maximum power transmitted. So this is standard formulas. And how to calculate the power at the sending end. So in order to calculate the power at the sending end, Ps plus jQs, which is also given as Vs into Is star. Why you put star? Because it has a real part and imaginary part. If we extend this Is in terms of real power is P plus J is going to be into Is is going to be this term, sine theta by 2 into Z0 into Im square plus Vm square by Z0. So this is the term for your Is, the reactive part of the current. So you have active power and this is your reactive power Q. So this is the reactive power. Then how to calculate a QS, which is a sending and reactive power. Sending and reactive power is given by P naught into sine theta divided by 2 within bracket P by P naught whole square, V naught by Vm whole square minus Vm by V naught whole square. So this is the formula. If you given a system, how much you want the reactive power needed to be calculated, you use this formula. So wherever I round it in a red color is the final formula you can use to calculate. Don't look at the theory too much to confuse. Theory is just few lines, but look at the final formula. This is required for if I have a system, how to calculate the reactive power requirement of a transmission line, use this formula. Then in case of midpoint, if I want to calculate in the midpoint of the transmission line, if I want to calculate what is the reactive power requirement at the midpoint between the generator and the load center, what is the formula? This is the formula. P naught into sine theta divided by 2 into P by P naught whole square minus 1. So this is the overall reactive power. You can measure either on the sending end or receiving end. You can apply this formula for calculating on the sending end. But if I want to measure at the midpoint, where is the midpoint of the transmission line? I have to apply this formula. It's okay. Then I'm going to look at uncompensated line under load with consideration of maximum power and stability. So when there is a what is the maximum stability, how I can look at the power. So in order to calculate the sending end power, the sending end power is sending end voltage. So sending end voltage is given by Vs into cos delta plus sine delta. So this delta is the torque angle or power angle of your synchronous machine, by adjusting which we can able to calculate. Of course, this formula can be represented like this: Vs cos delta, which is equal to Vr cos theta plus Zc into Qr by Vr into sine theta. So this is another way of representing this part. From this equation, I can able to calculate what is my receiving end power. So receiving end power is given by receiving end sending end voltage into receiving end voltage divided by Zc in sine theta into sine delta. So if you are going to neglect all the losses, this is the formula for calculating your receiving end power. Then if you want to calculate more compact way, in order to make it more compact for a short line, you can take sine theta equal to theta, which is nothing but beta L, where L is the length of your transmission line, and beta L can be calculated by omega L into root LC. So you can calculate for a transmission line where you want to have a maximum power and stability for an uncompensated network, you can apply omega L root of LC. From this equation, I'm substituting all into the power. I can find my receiving end power is approximately equivalent to Vs VR divided by XL, not Zc in sine theta, only XL into sine delta. Or this part is already, we know it's a maximum power, P max into sine delta. So in order to calculate the maximum power of an uncompensated network for the stability purpose, The P max is given by Vs VR divided by XL. So this equation is very important. It's clear to you? Can I go to the next one? So these all are the calculation formulas. I'm not giving you any derivation. Please note, I didn't derive. If you want to learn the derivation, please have a look on your textbook. I given only the final results. How to calculate your maximum power for an uncompensated line under consideration. Then compensated, why we are going for compensation? That's very important. What we are going to do with the transmission line compensation. So in order to make a very good flat voltage profile, constant voltage profile, I want to make my transmission line also compensated. Other one to improve the stability, because I want to transfer the maximum transmission capacity. I want to make it the transmission line more stable. For these purposes, in order to make it more economically beneficial, I have to use a different compensation. One is virtual Z compensation, virtual Q compensation, and compensation by sectioning. So these three methods are used in practice in real time for the transmission line compensation. One is virtual Z, virtual Q, and the third one is the compensation by section. The compensation can be done in different way. I can go for series compensation or shunt compensation. By using series and shunt compensation, what is the meaning? You know, shunt is connected in series with the sending and receiving end. Shunt is a parallel. So series means series connection. Shunt means parallel connection. I make, what is the benefit? Again, I can transfer maximum power or increase the power capacity. I can able to make the power transfer capability by using angle delta very easily. And of course, I can able to increase the virtual impedance, surge impedance. So these are the advantages by going for a series or shunt compensation. So how to calculate subsynchronous resonance? Very, very important in a transmission line. So I go directly with the formula. How to calculate the natural frequency F naught? You know already the standard formula, 1 divided by root 2 pi, root of LC is the standard formula. But in the transmission line, you will have inductance due to the line, inductance due to the generator, inductance due to the transmission. So we have three inductance due to the line cable, due to the generator, due to the transmission. You have to include all. Then the formula is not 1 by 2 pi root of LC. The formula is this one. Then from this formula, further I can substitute and extend by values like XL is 2 pi FL, XC is 1 divided by 2 pi FC. When I substitute all these in this equation become 1 divided by 2 pi root of XL divided by 2 pi F into 1 divided by 2 pi XC. Further, if I simplify this equation, is become F root of XL by XC. So this is the formula for calculating the rated frequency of a subsynchronous. It's very important because, for example, if your frequency is less than the subsynchronous, the series compensation will occur in subsynchronous frequency. That's very important. Another important aspect is your X by XL by XC ratio. So your XL by XC ratio decides the degree of series compensation between the range 25% to 65%. So the XL by XC ratio will give the degree of compensation with respect to 25 to 65%. Can I go to the next one? So this is very important, the subsynchronous resonance. Then I want to go for an important terminology, which is a subsynchronous resonance with generator. So you know the general model of your synchronous machine. I'm not going inside. So this will have a armature resistance, reactance, and you have the rotor due to the slip. This is the standard equation of your circuit model of your synchronous machine. And you know the slip is calculated F naught divided by F divided by F naught. So is a no load, full load divided by no load. So you get the slip formula. So in the if you get F naught is less than F, if your F naught is less than the natural frequency, then the slip is negative. You will have more negative damping in your system. So it requires voltage profile to be needed to be upgraded. So in this case, it's very important. In case of your SSR, which is already I discussed, subharmonic, I already discussed. Subsynchronous resonance is very important because it decides XL by XC ratio between 25 and 65%. And obviously, if you get F naught less than F, then the series resonance will occur at your subsynchronous frequency. So these are the challenges we need to maintain in your power system. So for this purpose, what we do, your generator will have electrical parts as well as a mechanical parts. So there is a interface of a torsional between your electrical and mechanical parameter with your synchronous generators. So what happen if this subsynchronous frequency increases? What happen? It can produce additional frequency in your torque that can interface on your shaft. Because of these additional sub frequencies, sub resonant frequency, you can break your shaft. This can happen in real time. So that's why we are going for compensation of subsynchronous resonances. So if this subsynchronous resonances makes a flow on your torque, the torque will become equivalent to your natural frequency. As I said in the example, you should not reach your natural frequency, the system will collapse. Any system in the nature. So obviously your shaft may break because of the twisting action. For example, if your shaft is rotating in clockwise direction, because of the subsynchronous resonance, it start rotate also opposite to the clockwise, anti-clockwise. So it can have a breakage because of this unavoidable situation of twisting. So in order to avoid this, we have to keep the control on your SSR, which is a subsynchronous resonance. It's clear to you? How to calculate subsynchronous resonance? It's this formula, and these two parameters are very important. Now I go for very fast presentation. If you have a good idea on power electronics, this is very simple. We have different types of compensation. One is a shunt compensation. What we are doing in shunt compensation is a parallel compensation. You can have a look. These are the blocks of a thyristors anti-parallel connected. So this is called thyristor controlled devices. So they are like not diode. A diode will turn on and turn off only during forward bias and reverse bias. But these devices, by controlling the gate signal by digital signals, we can make on and off in 50 hertz or 60 hertz operation. And they are connected in anti-parallel, 1 block, 2 block, 3 block, and floor block. And they are controlled by using a digital controllers. And the digital controllers having a parameter reference voltage, auxiliary input is required like speed, etc. Then this is the parameter settings we give, and we control all these thyristors to control the capacitor value. So by controlling this one, we vary the value of these capacitors. By controlling this two thyristor, we can vary the values of these capacitors. And this is inductor. We can also vary the values of the inductor. So they are called, these are called as a reactor bank, and these are called capacitor bank. When you control with the thyristors with the reactor, we call it as a thyristor controlled reactor. So these are called thyristor controlled reactors, and these are called thyristor controlled capacitors. Finally, they are all coupled to the transmission line through a transformer. You can have a look. So this is going to be a step down transformer because they are low power. This is very high power, high tension. So use a step down transformer. We connect here. And if there is any reactive power, we can store in the capacitors. And of course, if you want to inject the power to the grid, you can take from the capacitor or inductors. We can pump back to the grid. So that is the advantage of using this shunt capacitor. And all these control algorithms are fixed here for controlling. And this is also isolated from this point by using a potential transformer. In detail, we can have a look individually. This is like you see, you have two anti-parallel connected thyristors connected in anti-parallel in series with the inductor. By controlling these thyristors, you can vary the L and you can control the reactive power. You can have a look here. This is the voltage profile and this is your load current profile. Since the devices are turned on, you can have a look. You get only this voltage and it stops here. Then you flipped or clipped all the negative voltages, you see. So you can able to control. So this is the operation is called a thyristor controlled reactor. If you use the instead of inductor, if you put a capacitor, then it is called a thyristor controlled capacitor. So in this case, you can have a look. So this is your voltage. You are sending in voltage. By controlling these devices, you can see the current is shifted to leading. You can make this current unity, lagging, everything by controlling these two devices. So you have absolute control on your current for unity power factor, lagging power factor, and leading power factor by using thyristor controlled capacitors. So where you connect the capacitors in series with anti-parallel connected thyristors. So what is the applications of using a TSCR? We call it as a thyristor control reactor. You can have a continuous control, no transient, and generation of harmonics. What is the advantage of going for a TSE? You get continuous control here also, no transient and generation of harmonics. That's the basic advantage of using two types of reactive component, which is connected in series with anti-parallel connected thyristors. So this is called shunt compensation. And next type of compensation is a series compensation. Why we are going for compensation, I already explained you in which stages of the transmission line. So this is the series compensation. Now what happened, you can have a look. This is my voltage generation from the generating station, and maybe this is a load receiving center. We put all the anti-parallel connected thyristor in series. You can have a look. They are connected in series with the supply and connected to the load. By controlling these thyristor, we are varying the capacitors in series and we control the voltage. So that's why they are called series compensator. And you can have a look how this control algorithm is done. You have a transmission line, you put a CT transformer, and by using PT, you are connecting to the controller. In the controller, you set what is a control input is required voltage or current. Then you set other parameters even from the generators, etc. All the parameters are given. Then they generate the control signal for the anti-parallel connected thyristors. Then you connect the inductors. These inductors will vary. Its value depends on the angle the digital signal goes into the gate signal of your thyristors, and you can able to compensate in series. Same if you are going to replace this component by capacitor, then we have thyristor controlled capacitor. You can have a look. So the same control algorithms. We use control inputs, parameter settings, same transmission line. Then we use a PT, we use CT. So this is used to measure the voltage. This is used to measure the current. Same applicable here. So CT we use to measure the current of the transmission line. PT used to measure the voltage. All comes to the system. Then we generate the digital signals for the turn on and turn off of these anti-parallel connected thyristors. Then they are having two inductors on either side and along the capacitor. So we change this capacitor value accordingly in series with the transmission line. We can able to control reactive power. So this system is called a series compensation because we are trying to connect all the passive components. The passive components are controlled by static devices as an active component. Now we are changing the value of C by using these thyristors. So they become active controlled capacitors. That's why they are called thyristor controlled capacitors. So in this case, for example, how the output power will be sending end voltage into receiving end voltage divided by reactance into sine delta. This is the delta we are controlling here. All the cases. Delta will be varies from 0 to 90 degree. Say I keep 90, it's going to be 1. If it is 0, 0 power. So we control these thyristors by using these angles. By changing each, I can able to vary the reactance XL minus XC. So these are used to eliminate the lines with overload. They optimize the load sharing between parallel circuits. They direct the power flow. So you can able to control these devices. You can able to direct the power flow from sending end to the receiving end. Of course, receiving end to the capacitors to store the energy. So you can able to control bidirectional power flows by using these controlled devices. The most advanced configuration today, what we follow in real power system, what is the future of the power system is going to be power electronics. And we are going to have something like this. This is already started in real time with ABB or big companies. They already started implementing UPFC. So this is a unified power flow controller. You have two converters. So this is if you look at this is the transmission line. This is the sending end. This is the receiving end. From the sending end, we connect with a shunt or parallel this converter. So we call it as also called as StatCam. So this is called StatCam. What is StatCam? When a converter is connected in parallel to the grid or the transmission line. When a converter is connected to a series to the grid. So this is connected in series. You can have a look. So this is a series transformer. So this is a series compensation. This is a shunt compensation. We bring both series and shunt into one picture. So this is called StatCam on your left hand side. On the right hand side, we have called triple SC. If you have a note, you can note it in your textbook. They will not give you what is called a triple SC, static series synchronous compensator. So this is called static series synchronous compensator. It synchronously work with the load. It injects the current. So in series, current is common, right? So it injects the current. In parallel, the voltage is common, so it can get the reactive voltages through this converter. All the AC will be converted into DC, and it can be stored in the DC link. Whenever there is a power demand, we can take the power from the DC link, we can set back to the transmission line as a parallel addition of voltage. Here we can inject the current. For example, if the load is creating a lot of reactive power, the current will flow from load to the supply arm, right? Then I will generate a current, equivalent and opposite current, which is a reactive current. I generate through this series transformer, and I can able to nullify. So I can compensate in series. I can compensate in parallel. So the parallel compensation is called StatCam. Series compensation is called triple C. This is called triple C, static series synchronous compensator. I can control my transmission. What is the challenge in present world? And this is controlled by a digital controller. What is the challenge in present role? Where to keep this UPFC, unified power flow controller, or unified flexible. This is also called as FACS devices. The researchers are going on, can I keep these devices on the sending end? Can I keep it on the load center? Can I keep it in the mid? Still now, we are working more on this topic, where to place these components. This complete shunt and series combination compensators together in a power system, either on the sending end, either on the load center or the midpoint. Most probably preferred is the midpoint. Many researchers finding the solution to keep it on the midpoint. Then I go for the basic principle of power flow. So you have a sending end voltage. This is your receiving end voltage. And you have a transmission line reactance, which is X by 2, X by 2. Then you may create active and reactive power in your system. This is a simple model. Now, how to control the power? V square by X in sine delta is a basic derivation from your synchronous machine, because all your generators are synchronous, where we assume VR Vs is equal to V. That's why sending end voltage, receiving end voltage become V square by X into sine delta. Now I'm going to look at the characteristics. Is the same characteristic of your synchronous machine. I don't want to explain too much. So on your X axis, we are controlling the delta from 0 to pi plus theta. On Y axis, I'm looking at the power. You can look at when delta equal to pi by 2, you get the maximum power, because sine 90. It's very mathematical. If you put sine 90, this term will become 1 and you get V square by X. If you are looking at other angles, for example, if I increase delta from 0 to pi by 2, my power start increases from 0 to the maximum. And this is an example where you can have V 2V square by X into sine delta by 2. If you have a power generation like this, the characteristic is something like this. It's shifted. The peak is shifted from the ideal condition. You can have a look. This is a characteristic where we have 2 times V square by X into sine delta by 2, not sine delta, delta by 2. If you put 90, it becomes 45 degree. So whatever you get peak here, it will be shifted 50% more. And this is the characteristics for V square by X into 1 minus K into sine delta. When you have a output characteristic something, you have the same power. You can have a look at 90 degree. The power output is 3 times more. And this is the characteristics where V square by X into sine delta minus A. If the delta is subtracted by an auxiliary angle A, then you can have a look. Your peak is shifted something like this. So this is the characteristic of your power angle characteristics, V square by X into sine delta minus A. So these are the different characteristics. You can have an idea how it can influence with your angle delta. Now I want to give an overall comparison. If you use a series capacity compensation, how to calculate P2. So we have seen the characteristic here, P2, P3, P1 and P4, 4 different characteristics, how it has been came. The first case is a series compensation. In series compensation, we have P2 characteristic. We already seen how to calculate V squared divided by XL into 1 minus N into sine delta, where N varies from 0 to 1 maximum. That's why we got this characteristics. You can have a look, P2. And this is due to shunt compensation, P3. When you have a shunt compensation, how to calculate 2V squared by XL into sine delta by 2. So your angle is divided by 2. So in this case, you got this characteristics, this one. Still the peak is shifted. You can have a look because it's 90. For here, it is not 90, it is 45 degree. Third one is a phase angle control. You can go for phase angle control. Here the formula is P by 4, V square by XL into sine delta minus alpha or A. So this is the P4 characteristic where you can able to control the phase angle of your output power generation. So we have seen different characteristics. This is the standard characteristic of your generator with delta V square by X into sine delta. Then we move to series compensation, shunt compensation, and phase angle control. So we have different controls by using these static devices, thyristors or MOSFETs or IGBT. We can able to control the power flow of your transmission line. Can I go to the next one? Just look at the formulas which I rounded. It's enough for your understanding of the power system. Then stability is very important. Next part we are going to discuss on the stability. In few slides it will be finished. Stability is very important for your power system analysis. So voltage stability is carried out by using load flow analysis. Already in the last semester, power system analysis, you studied many load flow analysis, I believe. So I don't go inside, but it's very important to look the characteristic of PV, power versus voltage. So this is your distribution line. This is the sending end voltage and receiving end voltage. On receiving end, we'll have active and reactive power. If you want to make it as an open circuit model, this is the open circuit voltage will be connected to a resistor, reactance, and you have the load. So this is an example of unity power factor load. Then we can able to calculate what is my sending end voltage. Sending end voltage is given by VR cos beta L, where L is the length of the transmission line. J into ZC into PR minus JQR divided by VR into sine beta L. And you can assume in this equation, if you are sending in current is 0, then your output voltage is Vs divided by cos beta L. If you assume your sending in voltage is 0 and your short circuit current value is equivalent to the sending and receiving end current, then I can able to calculate what is my short circuit current, which is Vs divided by sine beta L. So only just have a look on the formulas, how you can able to calculate stability index analysis for your given power plant. Then we are going to look at the characteristics. That's very important. So we are going to look at the characteristics, the variation of PL by PC, the x-axis, and on the y-axis we have VR by Vs. And the same, we are looking for lagging power factor and leading power factor is the same ratio. Now you can have a look after the things, the ratio comes down. It's not 1.088, it's 1.05. You can have a look. The previous case, without the compensation, we have seen 1.088 is the ratio between your receiving end voltage to sending end voltage. But now it comes to 1.005. It's the only difference. So how to calculate your maximum power? It can be calculated by open circuit voltage square into short circuit current divided by 2 times 1 plus cos phi. And for this condition, we are considering the lossless line. So R equal to 0, G equal to 0. Then you can able to calculate your sending end voltage at any distance. For example, this X represents distance 100 meter, 200 meter, 1000, any parameter which is given by the standard formula. So we already seen this equation, and beta is in phase constant, where beta is a phase constant variable. Can I go to the next one? Then the concept of voltage collapse. This is the last part of our today's discussion. So voltage collapse will happen in any power system under different conditions. So that's very important how to identify. So in order to identify this system, we are considering a power plant. You can have a look. This is a sending end voltage. This is a distribution line, and we have a receiving end where we have a reactive power QR, and the load is considered as a reactance X, purely a reactance. Then in this case, in order to understand the system much better, easy, we are considering a lossless system. So P equal to 0, delta equal to 0. Then you can express from the previous equation of your receiving and reactive power. Now Vs VR divided by X minus VR square by X. Now I'm going to make it a dQr divided by dVr equal to 0. The rate of change of your reactive power on the receiving end with respect to the voltage is 0. Then I'm going to solve this equation. I can able to find your Qs. I go directly to the answer. Qs is equal to 1 divided by 2 Vs square by x plus or minus Vs into root of Vs square by x minus 4 Qr divided by x. This is the equation. So finally I find, but I want to find the differentiation of it. So I find the differentiation. I find the resultant something like this. So if you want to maximize, you want to put a Vs is equal to 2 times PR. Then this term will become maximized. And in this term, I can able to further reduce this term as 1 divided by root of 1 minus QR divided by Q max. So reactive power on the receiving end divided by Q max. So how to find the voltage collapse indication? This derivation is very important, this derivative. So dQs by dQr is a known voltage collapse approximate indicator. We call it as VCPI. So based on this value, it's very sensitive. You can able to identify, predetermine if there is going to happen any voltage collapse in your power system. So if you want to, as a power system engineer, you are going to predetermine the voltage collapse, you need to calculate this value. And there are certain guidelines based on which this parameter will be maintained on the ratio of your, please note this ratio purely depends on the reactive power received on the receiver side divided by the maximum limit of your reactive power. That's why in the beginning of the presentation, I said all the compensator should not exceed the maximum value of your reactive power capacity ratings. So this equation is very important to determine your voltage collapse indicator. We call it as voltage collapse approximate indicator, VCPI. Please have a look on this equation that can help you a lot. Finally, I want to look at the characteristics. We already seen the characteristic of PV. Now we are going to look at the characteristic of reactive power versus the voltage. So in the x-axis, we have a ratio of Vs by VR by Vs, receiving end voltage divided by sending end voltage. On the y-axis, we have Q, which is a charge represented in terms of reactive power, QR receiving end reactive power into reactance divided by Vs square. So we calculated and we plot the characteristic. You can have a look as your V is increasing. The ratio of your VR by Vs is increasing. Your charge, you can have a look. I say around 0.6 later, you get the positive charging. Look at the characteristics. All inverter hyperbolic equations, you can have a look as a V increases for particularly in case of 1, it goes to the maximum. You can have a look, maximum charges. And this characteristic decides how you can able to maintain or normalize your reactive power. So we are not interested in these areas. So the minimum requirement is 0.6. Then we are looking at the characteristics of your Q reactive power versus source voltage, sending in voltage. You can have a characteristic if Q varies 0 to plus Q, 0 to minus Q. You can have a as a Q increases on the positive cycle. At 0 Q, you'll have the maximum Vs. As Q increases, it drops down. You can have a look. Whereas on the negative side, Vs will start increases. So the gradient is minus Vs divided by S into SC. So it's a short circuit subsistence. So you can able to calculate your gradient. How to calculate your voltage stability analysis? So P is given by Px divided by Vs square. Q is given by QR into X divided by Vs square. And V is given by VR by Vs. So these are the index we use to calculate this normalized curve for which we can able to calculate the optimized value of your reactive power. So in critical loading condition, what we do, we take all in per unit. So P equal to 1 per unit will be taken for a critical load. So this is the like in case of your voltage stability analysis, two important curve is very important. One is PV, power versus the voltage, and reactive power versus the voltage. This is very important curve to decide the voltage stability of your power system. Then the last one is the voltage index stability. How to determine the deviation? So this is my sending end voltage. This is my receiving end voltage, and the corresponding the power is shown in active and reactive power. From this, I can standard equation. I'm not going to discuss on this equation. You can have an idea because you can easily calculate. From this equation, I have a real power. So this is the real part of the equation, and this is the real part of the equation. From this, I can able to calculate what is L, inductance per unit. The inductance per unit is given by 4 into Px minus Rq divided by Vs square whole square plus Rp into Xq divided by Vs square. So this is the complete inductance in per unit. For the stability index, please note your system is stable if L is less than or equal to 1. So in order to understand the voltage stability of your transmission system, you should be able to calculate what is L in per unit, and the L in per unit must be less than 1. Otherwise, your system is not stable. It's clear to you? So don't look at all these derivation. Is a basic equation. These are very basic equation. How to calculate this current? This current is nothing but sending end voltage divided by receiving end voltage divided by impedance. That's why I calculated this. So this is nothing but V by Z. V by Z. Then from this, we can able to calculate what is active power and reactive power. Active power on real part, reactive power on the imaginary part. Then we solve this equation. We have this equation, we solve it, and we are trying to find what is L from the equation. We got the L. So for you is very important how to calculate per unit voltage index stability by using L per unit. So this is the formula you need to use, calculate, and check whether it is less than or 1. Can I go to the next one? So with this, I completed today's important topic, which is very, very important for power system: load frequency analysis, advanced load frequency analysis, and of course, analysis on control algorithm. Of course, the reactive power compensation is very important. We have seen many compensator. We have seen series and shunt compensator. In case of switched shunt compensator, it is simple in principle and construction. It can use a fixed value. We use the switched shunt capacitor. So this is an inductor. This is a capacitor. So switched shunt reactor means inductor. We connect inductor in parallel. Here we use a capacitor in parallel. Both the cases, the principle is simple and construction. But in case of capacitor, you need to fix the value for the transient. It's very important because capacitor are very sensitive for transient. If you have a small variation in your current, it can damage very easily. That's very important. So they are used for over voltage protection, subharmonic filters, but they are limited with large capacities. We can't use for large transmission systems. And series capacitors, yes, the principle is very simple. Very relatively, we can locate in the sensitive locations, but the maintenance is very high because it's connected in series. You'll have the same current of your source. So the response will be very less. Then we have seen synchronous condenser. It can be fully controlled for low harmonics. That's the advantage. But the sensitive issue is where to find this location. And a very strong foundation basics is required. Complete detail is required to use a synchronous condenser. Then we seen polyphase saturated reactors. So polyphase saturated reactors are very effective because they don't have any effects on fault. They are well protected. They can be used for overload capacity, large capacity networks. They doesn't have any harmonics. And a disadvantage, it is also very difficult to identify the location where to place and what is the value, and it creates some noises. Then we have seen power electronics based systems like thyristor controlled reactors and thyristor controlled capacitors. They are very fast because they are controlled by digital circuits like DSPs, FPGAs, etc. And they can be very effectively during failure condition. They can be effectively run. And the disadvantage, they have a harmonic sensitivity because they are very sensitive to harmonics. Similarly, for a TSE, it can be repaired or can rapidly work under faulty conditions, and no harmonics can be generated. And disadvantage, obviously, it requires large capability for limit the over voltage conditions because the capacitors are very sensitive. So they are not very good inherent capacity absorbing large capacity over voltages. And of course, their working principle is very complex, and controlling the subsynchronous or low frequency resonance in the system is also complex. Overall, it's very sensitive to location. So this is the comparison what we have seen today's presentation. With this presentation, I finish. If you have any doubts, I'm happy to respond. On this topic, I have few problems. With this, seeing this problem, we can wind up today's lecture. That's very important. All basic problems, whatever you studied, your circuit theory, power system, same comes here. The problems are very, very flexible for you. I selected, but at the same time, it should be technical. We have a star connected 400 HP in metric machine, synchronous machine with a 2000 volt, 50 hertz motor, work at unity power factor of 0.7 lakh. So we given all the details, power factor, power and frequency and voltage. The bank of the mesh connected condenser is used to raise the power factor to 0.9. I want to improve the power factor from 0.7 to 0.9. Calculate the capacitance of each unit and total number of unit required. If the unit is rated for 400 volt, 50 hertz, the motor efficiency is given 90%. So you can have a look how the system is there. And we want to improve the characters. Please calculate along with me, otherwise it's very difficult. So we know the motor output power, which is 400 HP. We have supply voltage 2000. So that is where V. And power factor without condenser. Without condenser means without compensator is 0.7. So we have the 0.7. From these parameters, we have, yes. Yes. I'm going to calculate what is my motor current. How to calculate motor current? You have the voltage, you have the power, HP into 746. You know the horsepower should be converted. So I multiplied by 746 divided by √3 into my supply voltage 2000 into power factor, which is 0.7, and multiplied by my 0.9, which is given in the problem. You can have a look. The efficiency is 90%. So 0.9 efficiency, power factor, your supply voltage into this standard formula, the basics of electrical machines. The same way we applied. Please note 746 is used because it's 400 HP. You want to convert it into watts. So we got the power, which is 136.73. So this is your motor current. So 1 HP is nothing but 746 watts. Okay. Then I'm going to calculate what is my active. Can you calculate and find the answer? Anyone? 400 into 746 divided by √3 into 2000 into 0.7. Are you getting 136.73? Okay, 136.73 ampere, we got it. Next, I'm going to look at what is my active component of the current at 0.7 power factor. How to calculate the active current? IA1, which is given by I cos phi 1. So I have current, which is 136.73, which is already calculated from the first step, multiply by the power factor, which is 0.7. Now I got 95.71 ampere, which is the active current. So remaining is the reactive current. Can you calculate the active current? How much? 95.71 ampere. Just multiply by the power factor. Okay. Now I'm going to calculate the line current taken by the capacitor. So I have the capacitors. You can have a look. I have to calculate the current for the capacitor installed for improving the power factor. So how to calculate that one? IC equal to IA into tan phi 1 minus tan phi 2. So how to do that? IA is already calculated 95.71 ampere. I have here into, I want to know what is cos phi. Otherwise, I can't be able to calculate tan phi. How to calculate cos phi? Cos inverse of phi 1. Phi is equal to cos inverse of the angle, the power factor. Because power factor equal to cos theta. What is theta? Cos inverse of power factor. So cos inverse of power factor is 0.7. So I substitute here 0.7 and phi 2 is my, I want to improve to 0.9. So I put 0.9. Now I got the current 51.28 ampere. Please verify, or you getting the answer? You're getting 51.2 ampere. Can I go to the next one? Now I got the current, but I want to calculate per phase. I'm right. Then only I can put per phase capacitor to improve the character, condenser or compensators. So I want to calculate per phase divided by √3, 29.61 ampere. Now I want to calculate what is a per phase impedance, a reactance, capacitive reactance. How to calculate per phase capacity reactance? IC equal to V divided by XC. So V is 400 divided by XC. Already I know IC equal to 29.61 ampere. So I can easily calculate what is my XC. XC is going to be 13.51 ohms. Can you calculate XC? (13.51 ohms), I'm right. Now I want to calculate capacitance. What is the formula for calculating capacitance? If you know the reactance, what is the formula for XC? XC equal to 1 by 2 pi FC. You calculate C. C equal to 1 divided by 2 pi F, 2 pi F into XC. (235.61 microfarad). I'm right. So 235.61 microfarad. So you got the answer. See the problem. They said now I want to calculate capacitance of each phase of the bank. Divide it by 5 because there are 5 banks. I'm right. So divided by 5, you get 47.12 microfarad. This is overall capacitance, but I want to calculate for the bank. I'm right. There are 5 banks. Divide it by 5. 47.12 microfarad. I'm right. You got the answer. That's it. Can I go to the next problem? Next problem is a similar problem, but a slight variation. Here we have a 3-phase 50 Hz 2500 volt motor develop 600 HP and the power factor is 0.8 lagging and the efficiency is 0.9. A capacitor bank is connected in delta now. Connected in delta across the supply terminal. So supply terminal is here. We are going to connect in delta. Okay. In delta. And the power factor is to rise to unity. We want unity power factor here. Last problem is in 0.9 power factor is required to improve from 0.7. Here we need to increase from 0.8 to 1. Each of the capacitor unit is built up of 5 similar 500 volt capacitors. So there are 5 banks similar like the previous problem with the 500 volt capacitor. Determine the capacitance of each capacitor. So let's solve the problem. Similar approach. So we know the efficiency of the motor, which is given 0.9. From the efficiency, I can able to calculate what is my motor input power, output divided by efficiency. I'm right because efficiency equal to output divided by input. So I can able to calculate what is the input of the motor is nothing but output divided by efficiency. Please calculate. Here 600 HP is given, so I need to convert it into what? You multiply by 746. 600 into 746 divided by 0.9. Are you getting 497.33 kilowatt? Perfect. Now I'm going to calculate the capacitor bank. How to do that? So we need to keep a leading power factor kVAR is required by the capacitor bank. So the P into tan phi 1 minus tan phi 2. So I know the value of the P input power, which is a 497.33 within bracket 0.75. You can have a look. Minus 0. You calculate like previous one. You know phi 1. How to calculate cos inverse of power factor. Power factor will cos phi. Cos phi 1 equal to power factor. You want to calculate what is phi 1 like previous problem. Cos inverse of your power factor. Your power factor is 0.8. I'm right. You have to find the tan. Then you'll get 0.75. Please verify. Here you have to calculate for power factor 0.8. Here you have to calculate for power factor 1. You know cos phi equal to power factor. Phi equal to cos inverse of power factor. So here it's cos inverse of 0.8. Here it's cos inverse of 1. That is your value of phi 2 and phi 1. Then you find tan, like previous problem. So every time they can't give you, here you calculated, you see, tan of cos inverse of 0.7 minus tan of cos inverse of 0.9. So here you have to put 1. Calculate. It will be almost 0. So that's why we got a 373 kVAR. Please calculate. Someone is turn on the. Someone is turn on your mic. Could you please turn off? I can't.
I would do that, but in Najodeke because
You can mute him.
Okay, it's done. So do you calculate what is the value of your kVAR of the capacitor bank? 73. 373 kVAR is verified. Now I want to divide it by 3 because there are 3 phases. So divide it by 3, you will get it 124.33 kVAR. Okay. Then I want to calculate what is my current through the each phase of the capacitor bank. How to calculate the current? IC equal to V divided by X. So V phase divided by X, which is also can be calculated by using 2 pi of CV phase. See the formula. So what is a XC? 1 by 2 pi of C, you substitute, you calculate 2 pi into 50 into C into 2500 amperes. So this is available here. Then you can be able to calculate what is kVAR required per phase, which is 1000 is the base value. You can have a look here. So V into V phase divided by 1000, you apply, you can easily calculate what is the total resultant in kVAR, which is 1963 49.41 C. Please calculate. Otherwise, it's very difficult. Please calculate. At the end, you'll get this value. We need to find the C. That is the question, I'm right. They asked you to determine the capacitance of each capacitor. Are you getting the same one? 1963495.41. Once you calculated this one, we already know there is a leading kVAR is supplied, which is 124.33 kVAR. So now you can equate these two parts. You can easily calculate what is C. C is going to be 633.32 microfarad. Once you know the value, just multiply by 5 because 5 they already given in the problem. Each has built up with 5 units. So you multiply with 5, you get a 3116.6 microfarad. Please verify. So we already calculated here kVAR 124.33 kVAR. We have to equate to this equation to find the C. This is kVAR. This is also kVAR. So we equate these. We find what is capacitance. The capacitance is going to be 63.62 microfarad, but we want for a bank. So it should be multiplied by 5. Each unit is going to be multiplied by 5. So this is one capacitor, but for a bank, you need to connect 5 in series. Can I go to the next one? If you all okay, I can go to the next problem. The last problem of today's discussion. We have 3-phase, 50 Hertz, 30 kilometer transmission line supplied by a load of 30 megawatt at power factor 0.7 lagging to the receiving end, where the voltage is maintained at 11 kV. The maintained voltage is 11 kV. The power factor is 0.7. The load is 5 megawatt and it's a 30 kilometer transmission line, 50 Hertz. The line resistance and inductance. So the line resistance is given 0.02 ohms. Line inductance is given, which is a 0.84 milliohms per phase per kilometer, respectively. The capacitor is connected across the load. Now we are connecting the capacitor across the load to raise the power factor to 0.9 lagging. See the figure. They given the figure. We want to raise the power factor to 0.9 lagging. Calculate the value of the capacitor per phase and voltage regulations. So they're asking you to calculate the capacitance and voltage per regulation. So it's a standard formula, very standard basics. Might be or done also not in terms of transmission line, same one in a vectorical diagram in circuit theory. So that's why I took the problem based on basics. So you have a look on this one. So this is the power. You have two different power compensations, QC and Q2. Totally you get Q1. So now let us solve the problem. You know the length of the transmission line is 30 kilometer, frequency to 50 Hertz, load by 5 megawatt at 0.7 lagging power factor, receiving end voltage. So the voltage what you received is 11 kV. Now the line resistance per phase is given 0.02 ohm per kilometer. So I want to calculate for the full length, how much per kilometer is 0.02 ohms. For full kilometer, multiplied by the kilometer is going to be 0.6 ohms. Please calculate. 0.02 into 30 is going to be 0.06 ohms. Then I'm going to calculate for the reactance, which is also for 30 kilometer. How to calculate reactance for 30 kilometer? X is equal to 2 pi FL into 30. U2 pi F is 50. L is given in the problem, which is 0.84 into 10 power minus 3. You can see the problem. They given the reactance, which is inductance, which is 0.84 millihenry per phase. So 0.84 millihenry into 30 kilometer, you will get the reactance is 7.92 ohms. Please calculate this one and verify. Don't ask every time how to calculate phi. I already said phi is your power factor, cos phi equal to power factor. You want to find phi is a cos inverse of your power factor. Then you have to take tan. Are you getting 7.92 ohms? Very simple basic problem. 7.92 ohms. Okay. Now I want to calculate what is the active component of my at 0.7 power factor, but I want to rise it to 0.9. That is the goal. At 0.7 power factor, I have the active power, which is the 5 megawatt. Now I want to calculate the reactive power requirement. How to do that? Active power into tan phi 1 minus tan phi 2. How to calculate phi 1? Tan cos phi equal to 0.7. Cos phi 1 equal to 0.7. So I can calculate what is phi 1. Cos inverse of 0.7 is phi 1. Cos inverse of 0.9 is phi 2. Then you take tan, you can find these values. Please verify, are you getting 2.6979 MVAR? So how to calculate phi 1? Cos inverse of 0.7. How to calculate phi 2? Cos inverse of 0.9. We have two power factor. I have to rise from 0.7 to 0.9. So first case 0.7, second case 0.9. First find what is phi 1, cos inverse of 0.7. Then take tan. Are you getting the answer? Here how to do? Take cos inverse of 0.9. Then take tan. You'll get 0.484. Are you getting? Then finally find the answer. Are you getting the power 2.679 MVAR? So once you get the power, it's already said in the problem, we have to calculate by the capacitor bank by 3. So divide it by 3, you get 293,893 kVAR. I'm right? Divided by 3. Now I want to calculate the capacitance, which the problem is, the question is the capacitance. So I want to calculate what is the capacitance of the per phase across the load. So what I can do, how to calculate, like the previous formula, the same one, V phase, I phase divided by 1000. So you know how to calculate. V phase is already given. So I phase is given by, again, V phase omega C. Substitute all the value. V phase is 1000 into 2 pi F into C into, again, V phase is 1000 divided by 1000. You get this value. Now, if you get these two, you can easily find C. Please find, are you getting 38013.271.11 C? Please verify. Are you getting the same answer? Perfect. Then equate the equation of KVR, KVR, and KVR. You find C. Find the value of C. Equate both the equations. Because you already calculated a 2, you see here, you calculated 293 kVAr. Equate this equation to this one. You find what is C. C is going to be 23.49 microfarad. Please verify. Are you getting 23.49 microfarad? Perfect. Now, the aim is to calculate the voltage regulation. First part is finished. We calculated the capacitance. The second part is voltage regulation. So you know the formula for calculating voltage regulation: sending end voltage minus receiving end divided by receiving end. See my slide. Vs minus Vr divided by Vr. So I need to calculate what is my sending end voltage. How sending end voltage? How to calculate sending end voltage? You can see the formula: Vr plus I into R cos phi 2 plus Jx sin phi 2. How to calculate receiving end voltage? Receiving end is given in the problem, which is 11 kV line to line. So you convert into phase divided by √3. You get phase voltage of your receiving end, which is 6350.85. Please divide it. 11 kV divided by √3. Are you getting? Then you find the receiving end. Only sending end is needed to be calculated. How to calculate? See my slide. There is a formula. Same formula I given. So we need to use this formula. I know the receiving end. What I have to calculate? I need to calculate what is I, what is car. Cos phi 2 is already known, so I can substitute that. Please note here it is cos phi 1. Change this one into phi 1. So now I'm going to use the formula. How to calculate the current? So how to calculate the current? So current is voltage divided by the power. So you 5 into 10 power 6. 5 already given in the problem. You can have a look. See the problem. 5 megawatt. See the problem. 5 megawatt is given. So 5 megawatt divided by √3 into, you have the power factor 0.9 and the overall MVA is 11 into 10 power 3. Substitute and find it. So we are calculating for 0.9 power factor. Okay. So power divided by √3 into your voltage, which is 11 kVA voltage, into your power factor 0.9. You are calculating for the current at 0.9 power factor. So this is your MVA, megawatt. I'm right. Power divided by √3 VL cos phi. I'm right. You are calculating. So the I is here. So √3. If you multiply this one, power equal to I into √3 V into power factor cos phi. So now I want to calculate current. So I is equal to power divided by, send all the terms, root 3, voltage is 11 kVA voltage on the receiving end, into power factor is 0.9. I want to improve 0.9, I'm right, not 0.7. Substitute all the value, you calculate what is your current with improvement on the receiving end. So it's going to be 291.59 ampere. Are you getting? Then I want to calculate what is my sending end voltage. Now I want to apply everything here. So my VR is this. I already calculated my receiving end voltage, which is 6350.85 volt, plus my I is 291.59 ampere into my resistance is 0.6 given in the problem, and cos phi 2 is 0.9 power factor, 0.9. Please put it here 0.9 because cos phi is 0.9. I'm right. I want to improve 0.9. I don't want to find cos phi because cos phi is 0.9 plus j 7.92 into sine of phi 2. So here I want to calculate what is sine phi 2. How to do sine phi 2? Cos phi is 0.9. Cos phi is 0.9. What is phi? Find the value of phi and substitute here. So sine of cos inverse 0.9. So you need to calculate what is phi 2 first. Phi 2 is cos phi 2 equal to 0.9. Calculate what is phi 2. Cos inverse of 0.9. For that you take sine. Then you can land up with this value. Are you getting? Did you understand what I'm saying? Phi 1 is 0.7. Phi 2, cos phi 1 is 0.7. Cos phi 2 is 0.9. So you need to calculate what is phi 2. Are you getting the same answer? Substitute all, solve the equation and find the value in imaginary and real, or imagine this is in a rectangular form, this is in polar form. You know how to do that. And from that, you just calculate what is the magnitude. The magnitude is 11,406.84 volt line to line. Now you find what is the sending end voltage when the power factor is improved from 0.7 to 0.9. So this is the voltage we got at sending end from the generator when the power factor is improved. Okay. Now I want to calculate regulation. How to calculate regulation? Sending end voltage minus receiving end divided by receiving end. So Vs minus Vr divided by Vr. What is the sending end? 11,406.84 minus receiving end is already given in the problem, 11 kV. 11 kV. So divided by 11 kV, you get 3.7% voltage regulation. You see the problem, receiving end already given in the problem. You didn't. Yeah, where the voltage is maintained constant at 11 kV on the receiving end. Where you want to maintain on the load side, I'm right. So the load side is the receiving end. 11 kV is given in the problem. You are calculating everything on the generating side, because generating side they didn't give nothing. You see, they given transmission line, they given the load power factor, but the load power factor needed to be improved from 0.7 to 0.9. They given the resistance and inductance of the transmission line per kilometer, per phase per kilometer. They never mentioned anything about generation. You are calculating the generation and you know the receiving end. This is the required constant voltage. So the formula is Vs minus Vr divided by Vr. Now you calculated this receiving end voltage. This is the formula you applied. You calculated here, which is 1140. So the drop is 406.84. You lost. But why you improved? Because of the capacitor. Additional capacitors, you improved from 0.7 to 0.9. Is okay? Did you understand or still you have a doubt? Okay. What is the receiving end voltage? Have a look here. The receiving end where the voltage is maintained at constant 11 kV. What is the receiving end voltage? 11 kV. What is the formula for calculating voltage regulation? Vs, sending end voltage, minus receiving end divided by receiving end. Yeah. So we want to know what is Vs. I'm right. How to calculate Vs? We already calculated here. This is Vs. Vr plus I into R cos phi 2 plus J x2. We calculate all the parameter here, we substitute and we find the sending end voltage. So I have the sending end voltage already in the problem they given. Okay, don't think this one. This is for per phase. When you are calculate, you have to use per phase, but here is the actual voltage. Okay, line to line. So the line to line is 11 kVA. This is line to line. You see, line to line. So line to line is 11,406.84 is the generated or sending end. This is 11 kV receiving end. You divide, you get 3.7%. Are you okay now? So then with this, I finished. If you have an online student, if you have a question, I'm happy to respond. Otherwise, this chapter, I suggest you to have a look on 9.1, 9.2, 9.3, 9.4, 9.5, 9.9, and 9.10 problem for your good understanding of the subject. All these are solved problem, very simple problems, few lines problems. Have a look so that you can make your skills in the basics better. If you have a questions, I'm happy to respond. Otherwise, I finish my lectures today. We will see the next week with the MATLAB models. Meantime, go to the Canvas. Could you see my Canvas? Could you see my Canvas?
No.
Okay. Go to Canvas. Before, could you able to see?
Yes.
Canvas. Okay. You go here. You can see there. Look at the last week presentation. Before going to today's presentation, just have a look on these models. There is a simulation file directly you can download. This simulation file is common for this one. And of course, for this week, what today I presented. But we will discuss this one next week because meantime, you'll have a basics. You will understand something. So look at the problems, everything uploaded here. You can download and work. Maybe there are some little type of typographic error that is good because otherwise you will not learn. You sit and learn. All the problems we discussed are solved now. And go to your textbook, have a look on the problems which I given you assignment, try to solve it. So this is the MATLAB models of the last week lecture. This is the MATLAB model of this week lecture. The solution is available here. In one simulation file, just have a look how to make a transfer function of your prime mover, inlets, and of course the turbine model, generator model, and how to create the feedbacks, etc. So just a simple basics. There are some example in your textbooks which are available here and here, and try to understand so that your understanding on the subject is better. Any question? Any questions? If there is no questions on today's discussion, I think we can wind up and look forward to see you next Tuesday. The last part of the power system analysis, how to model your generators, prime mover, and hydraulic, hydropower plant design on based on equations. We will have an outlook, but next week you'll have a look on MATLAB. Meantime, have a great week and see you. Bye.
Thank you so much. Bye.